An example implementation of a virtual inductance or simulated inductor is discussed in this analog circuit design video. The circuit is implemented with one operational amplifier, one capacitor C, and one variable resistor RP that can be either analog potentiometer or digitally adjustable resistor RDAC. We want to see how the circuit works and what are the conditions that need to be satisfied for the proper operation of the circuit, so that if those conditions are met, then when the input impedance is measured from the perspective of this port, then the circuit behaves as if we have an inductor. So that's why we refer to it as virtual inductance or simulated inductor, because it really doesn't exist. It's just virtually simulated effectively. And I'm going to show the value of this inductance, virtual inductance, is L equal to R times, where R is this resistor connected to the positive and negative input terminal of the op-amp. And the small r is just the 10 ohm resistor for stability to make sure that the current flowing through this branch is limited current. And then RP is the value of the potentiometer or adjustable resistor. And finally, C is the value of the main cap in the circuit, that effectively we can say circuit is converting this capacitance into an inductance. Hence, we have an example of an impedance converter circuit here. Okay, let's see how this works. One note, of course, the selection of op-amp is important. It depends on the application. One example of that, of course, many examples available from Analog Devices and Texas Instruments, but one recent one, as recent as 2021, is this OPA X607, a 50 megahertz CMOS op-amp. That is exactly what we need, because the preference is having a near zero offset current, which CMOS op-amps pretty much satisfy. So depending on the application, we need to make sure that the proper op-amp is selected. Now, for this op-amp, let's make the assumption that the supply voltage is plus minus 10 volt, for example, applied. Output is connected via resistor R to input negative or inverting terminal, indicating negative feedback, and therefore what I can write for the op-amp, obviously, is I can write just op-amp is in linear region and enforced by negative feedback. And therefore, we are benefiting from virtual short, which means that the negative feedback will enforce the voltage at positive and negative input terminal of the op-amp to be the same, equal to Vx, let's say. So we have effectively Vx here at this node, and we have Vx here at this node as well, virtual short. There is no voltage drop across R because the resistor R has a current that is nearly zero. So the current here is nearly 0 microamp because the input impedance of ideal op-amp is practically infinite. The same goes here as well. So there is nearly zero current flowing, especially with the CMOS operational amplifier that we are selecting. Now, if we want to measure Zn, then the traditional and the general method, the established method, is we apply test voltage. So we apply test voltage V test, in which we know the value of the test voltage, and then we need to measure the resulting test current flowing through the circuit, so that then we would say Zn, or input impedance, is equal to the applied voltage V test divided by the resulting current I test. So I need to find this Zn. This is my equation 1. Okay, so another observation is this, writing a KCL or Kirchhoff current law here, the current entering, which is I test at a node, should be equal to the sum of the two. In this case, we have two branches out, so sum of the resulting two currents outward, I1 plus I2 equal to IT. So I'm going to write it as well. I test equal to I1 plus I2. That's just a purely KCL. So circuit law, basically. So then let's refer to this as equation 2. Okay, next step. Since the current that is going through the positive input or non-inverting input terminal of op-amp is 0, we can make the assumption safely that C and R, as highlighted, the cap C and resistor R, are effectively in series. Therefore, I can easily find I2, given that the voltage at the input is the known voltage Vt. So I'm going to write it here. So let me just write it here. So I2 is as simple as V test divided by R plus 1 over Cs. the series of the two resistors. Okay, so let's refer to this one as equation number 3. I can do the same thing in the sense that utilizing the effective series of C and R to do a voltage division via KVL and find the Vx as a function of Vt. It's just a voltage division. So I can say Vx is equal to just simply R, this resistor, divided by the series of R and cap, which is R plus 1 over Cs, times the input voltage, which is Vtest. Okay, so let's refer to this as equation number 4. Now, for the series of R and Rp, in which, as I said, R is a small resistor to limit the current I1 to a practical level, and Rp is a potentiometer variable resistor, for example, 100 ohm. If that is the case, then it means its value is changing from 0 to 100 ohm. I'm going to talk about the choice for Rp, but with that said, since I know the voltage drop across this series, one side we have Vt, which is the left side, and on the right side we have Vx. Therefore, I can find I1 easily. So I'm going to write I1 is equal to the voltage drop across the series, which is Vtest minus Vx, divided by the series of small r plus the capital Rp, which is the potentiometer. Now, in this equation, I'm going to substitute for Vx using what I found in equation 4. So using equation 4, it becomes 1 over R plus Rp times Vtest minus, and then Vx here is just R over R plus 1 over Cs times Vtest. So further simplify, what I'm going to get out of this equation is as simple as I1 is equal to 1 over R plus Rp, and in numerator and the rest of it we have just simply 1 over Cs divided by R plus 1 over Cs and then times Vt. So let's refer to this one as equation number 5. Okay, what else we can write? Well, we found I1, we have equation 2. We found in equation 3 I2 as a function of Vt. We found in equation 5 I1 as a function of Vt. So basically what I can do is I can say, let's combine equation 2. Basically in equation 2, let's substitute for the value of I1 and I2 from using equation 3 and 5. So using these three equations, I can say I test is equal to I1, which is the one that we have here, plus I2, which is here. So I can factor out Vt divided by R plus 1 over Cs to make life easy. So Vt divided by R plus 1 over Cs, and the rest of that becomes for I1, we have just simply 1 over R plus Rp times Cs in denominator. And for I2, we just have 1. That's it. Okay, so what is the next step? It's going to be as simple as saying IT, or let me put it this way. It would become Vtest. So basically it would become Zn, or the input impedance of this circuit is Vtest over Itest is equal to, I can say 1 plus RCS in numerator, and in denominator we have this denominator. So again, in numerator we have also R plus Rp, and in denominator we have just to make sure I'm not making a mistake here, it will be 1 plus R plus Rp times Cs. Okay, so what is the outcome? We found the closed form formula for input impedance of this circuit, and it doesn't exactly look like an inductance. Well, here are the little quick assumptions we're gonna make, and that would actually be just the point we need to have. So if I make this assumption that RCS, so here are the assumptions I'm gonna make, which are very practical assumptions as a part of my design. So RCS, especially for the range of frequencies. So let me put it this way: for the range of frequency of interest as the frequencies of operation of the circuit, so basically when I substitute S equal to J omega for the range of omega, then what I'm trying to say is I want effectively 1 plus RCS to be just RCS. So if I have absolute value of RCS much, much larger practically than 1, then I can say numerator of here becomes simply, I can neglect 1 effectively, and I can just RC times, so I can write it this way. I can write R plus RP times RCS in numerator. And for the denominator, if I can make the assumption that 1 is actually much, much larger than, I mean, considerably, practically larger than R plus RP times CS, then denominator effectively becomes 1. So we are done. If these assumptions are in place, then it means the whole Zn, the whole equation we have here, converts to, simplifies to, is simplified to Zn equal to, so Zn is practically just R plus RP times R times C, and then we have S. That's exactly what we wanted to find. See what I found? I'm gonna copy paste the formula that we have, and I'm gonna just put it here side by side. So there you go. This is what we wanted to prove, and we got it, because this is exactly L multiplied by S. So the input impedance of the circuit really looks like LS, which is the impedance of a simulated inductance, even though we don't have a real inductor in the circuit, but effectively we sort of realize a simulated inductance, but we need to satisfy these conditions. So what are these conditions effectively? These are, so we proved that the circuit can really operate as simulated inductor or virtual inductance. Just we need to satisfy these things. What are these? So for these conditions that I'm going to highlight, effectively in sinusoidal steady state analysis, we have S substituted with J omega. So what are we saying from these conditions? We are saying RC J omega absolute value, which becomes RC omega, should be much larger than 1. So let's say RC omega is greater or equal 10. That's good enough 10 times. And then we are saying 1 should be considerably larger than R plus RP, let's say CS or CJ omega. So the same thing here, absolute value. So C omega, which let's say practically we are saying let's say R plus RP, let's say C omega should be less than or equal 0.1, so that it's considerably less than 1. Okay, so what are we getting out of this? what are we getting is now I can form omega in this case, and I can say for omega we have, or omega is 2 pi f as well. So 2 pi f, in which f is frequency in hertz, omega is in radian per second. So what I can say is I can end up with computing that the frequency of operation for this simulated inductance should be just in the range of, let me just put it here. So should be in the range of, let me just make sure that I am not missing anything. Okay, so that frequency should be in the range of 10 divided by 2 pi RC, and less than or equal 0.1 divided by 0.1 divided by R plus RP, and then times C, and then 2 pi. Okay, so if in this circuit C, for example, is set to be 10 nanofarad, as an example. So if we set C to 10 nanofarad, and let's say if we set RP as 100 ohm variable resistor, so what happens is, of course, assuming that we set RP to its max value, let's say this series of R and RP becomes 110, so we end up with, so I'm going to set it here, RP 100 ohm, C 10 nanofarad. Then here's what we're going to get. We're going to get F is less than or equal 0.1 divided by 2 pi times 110 times 2 nanofarad, which 10 nanofarad, which is 10 to the power minus 8, and greater than or equal 10 divided by 2 pi. Let's select R to be 10 mega ohm, for example. So the same thing here. It's a safe assumption because then again, with proper selection of the op amp, then the input current is negligible to the current going through 10 meg. So we have 10 pi, 2 pi, and then we have 10 meg, which is 10 to the power 7, and then C, which is 10 to the power minus 8. So what is the lesson learned? So the lesson that we learned from this exercise is F is greater than or equal, let's say as an example, we have in denominator, what we have is we have 10, and then divide by the value we have, we get just say 15 hertz. And for the other one, what we're going to get is the value of roughly, we're going to get a value of, say, 10 to the power 5 divided by 2 pi. So it's going to be 15 kilohertz. So basically what we designed with these choices and examples, like if we go with 10 nanofarad cap, and with 100 ohm the value of this RP, and 10 mega ohm the value of resistor R, then this circuit is able to implement a simulated inductance at the input as shown, because the measured Zn is now for the range of frequencies that are found here is going to be this value. So in this range, then the circuit behaves like a practically behaves like an inductance with a value of, say, measured value, let's say, of 10 meg times cap of, we have 10 nanofarad, which means 10 to the minus 8 farad, and 10 meg means 10 to the 7. And then R, as I said, is 10, and RP is adjustable. So the value of inductance effectively turn out to be just a sizable value actually. So it will be, say, inductance is realizable between RP can be 100 ohm and 0. So if RP is 0, then the value of inductance that is realized is going to be just 1 Henry. And if RP is 100, then the value of inductance is going to be 10 Henry. So that's the interesting outcome of this circuit. Okay, I hope that this example is helpful in terms of showing how such virtual inductance realization work and what are the conditions. So we need to just make sure that the frequency range of interest is properly satisfied by the proper selection and choices of the components in the circuit. I hope this is useful. Thanks for watching.